Chapter 31. Chapter 31 is all about radioactivity. And where do we use radioactivity in everyday life? A lot of places. Where do you use it in medicine? Radiation? What do you mean radiation? With cancer? So what do you do with radiation with cancer? Target bad cells with what? Radiation. What kind of radiation? What do you shoot at bad cells to kill them? Do you know? You got computers open. Check your computers. What radiation kills cancer cells? So a bit louder.
Oh, is it X-rays, gamma rays, electron beams, or protons?
Electrons and proton beams. Those are new technologies, and then gamma rays will kill stuff. So that's radiation to kill these things. So that's not quite the same as radioactivity, but you do use radioactivity in medicine. Where do you use radioactivity? Any ideas? You haven't learned this in your classes? Your teachers are horrible, all of them. Go tell them. All your health sciences faculty that I have to work with, tell them they're awful. So radioactivity, sometimes when you have to get MRI and they need to see your internal organs really, really clearly, sometimes, have you ever seen an MRI before? They're very hard to discern what pieces you have inside of it. So they need to do something to make different pieces stand out more. What can they do to make things stand out more? Contrast. How do they get that contrast? What do they make you do? If you've ever had an MRI, yeah. Like a liquid. They make you drink like a huge jug of really nasty tasting liquid that has radioactive properties. So that makes you glow differently on the inside and the MRI. So they can get better contrast so that they can see things better. Okay. Other places we use radioactivity, we use them in nuclear power. Nuclear power, is that safe or dangerous? We'll see about that. Okay, so radioactivity. Some equations that you'll need to do your homework. This is just a review equation. What equation is this? I should record your answers for Dr. Iyer. Let's do that. We're gonna do a plan. So we're going to test the Physics 162 students and see if Dr. Iyer deserves to keep her job. We're reviewing radioactivity. This is one of the most important equations in radioactivity. What does that equation give you? What is it? Kinetic energy. Kinetic energy, 1/2 mass times velocity squared. Congratulations, Dr. Iyer. You are still employed. Okay, kinetic energy, 1/2 mass times velocity squared. Okay, so you can calculate kinetic energy of different particles by calculating what their mass times their velocity squared is. And you're going to do that. And there's different kinds of particles that you'll be using. You'll use things called alpha particles, beta particles, all sorts of stuff. And what you're going to use primarily to do this kinds of calculations is how they work in radioactive kinds of processes. So to understand these radioactive processes and the way radiation works, radiation is basically an atom changing into another atom spontaneously. And there are ways that that happens. To understand this and to actually work with it, you need to understand first something called a nuclide. Nuclide is a way to write stuff about elements. And where do you go when you want to know any kind of information about an element? periodic table. That's the first place we go. Everybody knows chemistry. Nobody ever knows answers to physics questions. All know stupid, useless chemistry. So let's write some chemistry. I'm gonna write X. I'm gonna write A. I'm gonna write Z, and I'm gonna write N. And this is a general kind of way that we write out information about nuclides. And each of these things means something different. A. What does A stand for? Uh-oh, I didn't write it on my notes. Yeah, that's the atomic mass. And that's equal to Z plus N. What is Z? Atomic number. Okay. The atomic number. What does that tell you? What is Z? Physically tells you something about the atom. Number of protons. Tells you how many protons are inside of your atom. And that's what defines an atom. An atom is defined by its protons. Sorry for locking you out. Fixed. Number of protons defines the atom. If I have 1 proton, what atom is that? Hydrogen. If I have 2 protons, what atom is that? Helium. 3 protons. Lithium. 4 protons. Who cares? Everything else is metals. We'd go to a periodic table and look that number up. Okay, we've got N. What does N give you? I actually forget what the technical name of it is, but it just gives you the number of neutrons. So to get the atomic mass, you're basically adding up the number of protons plus the number of neutrons. What about the electrons? Well, first, how many electrons are in that? Can we tell that based on this? Yeah, typically the number of protons is the same as the number of electrons. So most atoms are neutral. And then when you start having different numbers of electrons, we give that kind of atom a name. What is that called? Not an isotope. That's called an ion. When we have different numbers of neutrons, what's that called? That's an isotope. Okay? That's atomic physics. Okay? And then X is actually the symbol for your element, whatever element you're talking about. And that's where the periodic table comes into play. So you'll need a periodic table to do most of these kinds of questions that you're going to work on. And there's a few different kinds of ways that atoms can spontaneously decay due to radioactivity. One of them is called alpha decay. Alpha decay involves something called alpha particles. Anybody catch from the lecture or from the reading? Because you all always do the reading. I'm sure you read the book. You've probably read it more closely than I have. Alpha particle. What is an alpha particle? Remember what an alpha particle is. Let's write down the reaction for alpha decay. We have an element X. Where do we go to get what X is? Let's say if I want alpha decay of carbon, where would I go to find out what X is? Periodic table and find out what is the symbol for carbon. Okay, and then I would plug in the number of neutrons, the number of protons, and the atomic mass. And if carbon or whatever element, whatever X element is going to go through and do alpha decay, it's going to turn into Y of n minus 2, Z minus 2, A minus 4. So Y is the new element that it becomes. So X, let's say X is carbon. What's the atomic number of carbon? Carbon is 6. Okay. So then, what would our new Z be if we go do alpha decay? If X is 6 for carbon, what does this become? 4. So how would I figure out what Y is? I look at the periodic table, and what number would I look for? 4. And replace that symbol with 4, whatever 4 is. I think it's boron. Okay. And then N minus 2, number of neutrons minus 2, A minus 4, A minus 4. So this is all pretty straightforward to do, as long as you have this general formula written out. But atomic decays have to be balanced. So both sides have to give you the same number. So if we're losing 2 protons, we need to have another particle that has those 2 protons still. That particle is going to be this. It's going to be helium. So this is completely general. Could be whatever element you want. And then it turns into this element plus helium. Helium is what's known as an alpha particle. So that's why this is called alpha decay. Because you start with an element, end up with another element plus a helium. Yes, sir?
So no matter what, we'll always be adding.
For something that has alpha decay. This formula works every time. So all you're doing in these questions is looking up these symbols and the numbers that go with them from the periodic table. And there's other kinds of decays you can have. There's beta decay. In beta decay, you end up with beta particles. So you have beta minus particle, beta minus decay. You start with A, Z, X, and N, whatever that is, and you end up with same A. You end up gaining a proton, so this Y is going to be whatever gains your proton. You lose a neutron, plus an inverse beta particle, plus this thing right here. We know what that is? It's atomic physics particle. That is something called a neutrino. That is a anti-electron neutrino. Every second, there are billions of neutrinos flying right through your face. Nope, right now, a billion neutrinos just flew through your face. Good. So we got this beta minus decay. We also have beta plus decay. We're going to start with A, Z, X, N. This is V. It's actually a Greek letter nu. Okay, so that's beta decay. Then there's another kind of decay that we'll talk about, electron capture. So this is where we gain an electron. So we do, this one's a little bit different. We've got our X, Z, N, A. And then what this is going to do, this is going to grab an electron. So what's different about this one than all the previous ones? What did you start with on all the previous ones? What was on the left-hand side? All the previous ones had this and only this. And they turned into a bunch of other stuff. This one starts with 2 things on the left-hand side. So this is going to grab an electron, and it's going to become Y, N plus 1, Z minus 1, A, plus an electron neutrino. So these decay, they're called decay reactions. I would put these general equations on your equation sheets for an exam and know how to use them. So when you're doing the homeworks, just use these general formulas and plug in. Right? It's kind of plug and chug. It's like solving a little puzzle. Boring little puzzle, but puzzle nonetheless. If you want a picture, that's the picture to take. That's everything to put on your cheat sheet. Any questions? Preguntas? No más preguntas. ¿Estás bien? Sí.